Hi guys, in this video I want to talk to you about basically explaining this demo. So if you didn't make it, I strongly encourage you to make the demo and figure it out for yourself. I'll also put a video link in the chat where Rhett Allen, he had his daughters play with this, and you can kind of figure out which one's harder to rotate based on that. But this one right here, it's not too bad to rotate it. This one over here, a little bit harder to rotate it. Applying roughly the same amount of turning effect to it. When the mass is farther away, it's harder to rotate. I like that demo because we don't really have much experience with how hard it is to rotate objects. And so like there's this concept behind this demo of what I want to call rotational inertia. You'll also hear it called moment of inertia. Conceptually, it's how hard it is to rotate an object. So just like we had rotational analogs of distance, velocity, acceleration, there's this rotational analog to how hard it is to sort of accelerate, to get an object to rotate and accelerate it, to angularly accelerate it, to rotationally accelerate it. So this is different than mass, though, because these two demos right here, they're of the same mass. The only difference here is how that mass is distributed relative to my axis of rotation. So in this case, the axis of rotation is directly to the center. I could theoretically rotate this on one of its ends, and that might change how hard it is to rotate. But the key idea here is relative to some axis of rotation, how hard it is to rotate an object depends on where the mass is distributed relative to the axis. That's the key idea. Depends on mass and how that mass is distributed relative to some axis of rotation. Now in this class, the axis of rotation is always going to be like through the object, but theoretically, like, if I was to rotate this object, relative to, I'm not going to even worry about that. The axis of rotation, though, is going to be typically through the center of it. But if you were to rotate an object not through its center, the key idea is that the rotational inertia will change. So it depends on the axis of rotation. There's usually like some main points of symmetry. So if you were to spin something, that would be one axis, one like principal axis. If I was to sort of rotate it like this, that's another axis. And if I was to sort of spin it like this, make sure not to get hit. So in those cases, there's like three different rotational inertias. Two of them are pretty similar, but different objects the same object has different rotational inertia depending on the axis. All right. I want to kind of motivate where the equation for rotational inertia comes from. And so let's think about a point mass. So a little tiny dot of mass rotating around some point. You can imagine that maybe there's like a string connecting it, keeping it moving in a circle. And maybe there's some kind of like rocket booster causing this thing to accelerate in the tangential direction. So it is accelerating. I'm going to say that the force I want to focus on is, let's say there's a force in this direction causing it to rotationally accelerate. We know that this like tension or whatever is acting in the radial, but I want to focus on what's causing it to rotationally accelerate. So let's just apply Newton's second law. If this is some point mass of mass m, Newton's second law, it's just going to be F equals ma. But if I want to sort of find the rotational version of this, how do I relate this acceleration to alpha? That's kind of what the goal is here. And out of that will come an equation for rotational inertia of a point mass. So if I rewrite m in terms of alpha, I know that when I take the radial distance and multiply it by alpha, that'll recover the tangential acceleration. And this F is a tangential net force. If I'm talking about rotational motion, I could, let's say, want to think about this in terms of turning effect or torque. So what I need to do to turn this F into a torque, I can multiply both sides by R. So this term on the left now becomes my net torque, and that is equal to m times r squared times alpha. So I want to just draw the comparison. The net force in the rotational, if I'm looking at this through a rotational lens, this is the analog of force, this is the analog of acceleration, and this right here is the rotational inertia of a point mass. So this is, we give the symbol I for rotational inertia. So to summarize, rotational inertia of a point mass. There's a nice equation for it. I equals mr squared. This is not on the reference table. This is something you do need to memorize. And what I want to just suggest is if you take an extended object, like not a point mass, you can think of it in terms of tiny point masses and add up all of those point masses to get an overall rotational inertia. So visualize some extended object, breaking it down into point masses, and then adding up those point masses using this equation. You can go to a mathematician to kind of get those calculations for symmetrical objects. They turn out pretty nicely. But that's how you'll get the rotational inertia of not just a point mass, but an extended object. In general, the rotational inertia is going to be proportional to some constant times mr squared, where r usually is like the radius of the object. So, let's suppose you have a sphere, a solid sphere, and like a hoop of roughly the same mass and radius. There will be some constant for a sphere, it's about 2/5, and there'll be some constant, I think it's like 1 for a hoop. And so I'm just going to put a little c there, some constant, some number. And basically, the higher that number, the more the mass is farther away. Some of the questions that I'll give you in your practice will ask you to sort of compare the rotational inertia of different shapes. And if you're assuming that they're the same mass and same radius, you can just think, hey, if this is a solid filled in sphere and this is a hoop, which one has more mass farther away? Should be this guy. So if you're thinking back to the demo, when more mass is farther away, it's harder to rotate. That's the whole point of the demo, kind of internalizing that. That is rotational inertia. I think I covered everything. Hope that was helpful.